In a previous lecture, we talked about the second law of thermodynamics, and in this part of the lecture, we're going to talk about calculations that you can do using the second law of thermodynamics. There are four general types of calculations you can do depending upon the conditions. For an isothermal change, we'll go back to these in just a minute, but isothermal, for non-isothermal processes, and then for isothermal volume changes, ideal gas, PV work, we have this, and the pressure changes, we have that. All right, so those are the four basic equations we're going to use to do some calculations with the second law of thermodynamics. Now, let's talk in more detail about this. This is isothermal change. Let's start from our definition of entropy. ds is TQ reversible for a reversible process divided by temperature. Let's integrate both sides. Let's integrate ds. S is the state function. This will be just delta S, the difference between the final and initial entropy. And this then will be the integral of dq reversible over T. So far, so good. And now let's make the assumption we have constant temperature, so we can pull that out. And this just be integral of dq reversible. And our assumption here is constant temperature. And we'll just call this integral of dq reversible the total heat transferred in a reversible process in going from the initial to final state. This is just q reversible over T. So if we have a reversible process, we just look how much heat we've transferred, divide by the temperature at that constant temperature, and that's the entropy change in going from your initial to final state. That's that one. Now, what happens if the temperature is not constant? Again, we'll start with our definition of entropy. Entropy is dq reversible over T, and we'll integrate both sides going from initial to final state, ds. This will be just delta S. This will be integral of dq reversible over T. Now, temperature is not constant, so we can't pull this out of the integral. However, we do know that for a reversible process, or in general for anything, the reversible is the heat capacity times the change in temperature, or since we're doing infinitesimal changes here, let me write this as d dt. So if that's the case, we can put that up there, change the variable of integration. So this now will be the integral of 1 over T times the heat capacity times dt. And let's make the assumption that heat capacity is a constant. We can pull this out of the integral. So be the heat capacity, the integral of 1 over temperature dt, constant heat capacity C, and the integral of 1 over T is just C times the natural log of the final temperature divided by the initial temperature. This is how you would calculate entropy changes if the temperature is changing. Let's go here. Let's see, put some more restrictions on. Isothermal volume, ideal gas, only PV work. Start again, once again, from ds is dq reversible, heat transfer in a reversible process divided by T. Integrate both sides, integrate ds. This will just be delta S, initial minus final minus initial. This is the integral of dq reversible over T. And now let's make it isothermal, constant T, 1 over T, the integral of dq reversible. We're integrating over that. Now we're going to make the assumption isothermal and only PV work. So isothermal, remember that du is equal to 0 for an isothermal process for an ideal gas. That's one of our restrictions here. This is dq. Let's make this reversible plus dw reversible. So this is an ideal gas, and that is equal to dq reversible minus pdv. The assumption here is only PV work. So in other words, dq reversible is just pdv. So let's go ahead and do that. So now we have delta S is the integral of dq reversible, which we just said was p dv, and we said temperature was constant, 1 over T, p dv. Here's pressure, here's volume. We need a relationship to integrate this, how pressure depends on volume. And by the way, we made the assumption of an ideal gas, constant temperature, and only PV work. That's how we got to this equation. 1 over T, the integral. Since it's an ideal gas, we know how pressure depends on volume. Pressure is just equal to nRT over V dV. Oh, that's nice. We're going to make an assumption of constant number of moles. We're not adding or subtracting anything into it. This will be 1 over T. We're pulling N and R and T is constant T. We can pull that out. So this will just be nRT, the integral of 1 over V dV. Note how the T's cancel out. So this is just equal to nR. Integral of 1 over V is just natural log final volume over initial volume. And that's where we get that equation. And then if we make the same kinds of assumptions, we can just immediately change this into a pressure change. Because we know for an ideal gas at constant temperature, V2 over V1 is equal to P1 over P2. For an ideal gas, this is Boyle's law essentially. So we can say that delta S is equal to nR times the natural log of, we're going to substitute in for V2 over V1, P1 over P2, and that's equal to minus nR times the natural log of the final pressure divided by the initial pressure. So that's that one. So those are where those four equations come from. We all start with definition of entropy. ds is equal to dq reversible divided by temperature.